In this example, we are going to use our formal definition of a topology to show that this particular collection of subsets of a space is, in fact, a topology. So this topology is called the finite complement topology. And in order to understand what we're talking about here, let's recall what we mean by the complement of a set. Okay, so we have this space X, and in that space we have some subsets. So this is some subset U of X. And the complement X minus U is all of this stuff that's in X but is not in U. Okay, so that's what X minus U is. And the finite complement topology is the collection of all of these subsets U whose complements are either finite or all of X. So let's take a look at what all criteria this collection has to satisfy in order for this to be considered a topology. So remember that our first criteria is that we have to show that both the empty set and the entire set itself are in the topology, right? So this is pretty simple because if I look at the complement of the empty set, I get the entire set itself, and which is all of X, right? So that works. And if I look at the complement of X, I get the empty set, which is finite. So we're good there. Okay. Our second criteria that we have to satisfy is that we need arbitrary unions and finite intersections. So I'm going to list these out and then we'll show them one by one. So we need the complement of arbitrary unions. Let me maybe make that U a little bit bigger. So arbitrary unions to be finite or all of X, and we need our finite intersections to have their complements be finite or all of X. So those are the last two criteria that we need to check, right? Okay, and maybe just to kind of reiterate why we're writing it this way. So remember, we're saying that these U's are the open sets of X, right? And our definition of a topology requires that these unions and intersections of U be in the topology. And we're saying that in order for something to be in the topology, its complement has to satisfy certain criteria. So that's why in order for these unions and intersections to be in the topology, we have to check to see if their complements are finite or all of X. All right, so let's take a look at criteria number 2 to start. So we're good with criteria number 1, but let's check criteria number 2. So recall De Morgan's laws. For complements of unions and intersections, because we're going to need those in order to show this. So if I take the complement of a union, what I get is the intersection of complements, and I'm not writing that correctly at all. So the intersection of complements. And if I take the complement of a union, I get, the complement of an intersection, I get the union of the complements. And this also works for arbitrary unions and intersections, which we'll see. And we proved that a couple of homework assignments back. Okay, so if I'm looking at the complement of an arbitrary union, by De Morgan's laws, this is equal to the arbitrary intersection of the complements, right? Well, remember that for the second and third criteria of a topology, these U's that we're taking the arbitrary union and intersection of are already assumed to be open sets in the topology, okay? So here, each of these U alphas is already in the topology for all alpha, right? So what that means is that x minus U alpha is either finite or all of x for all alpha. So this is either finite or all of x for all alpha. Okay, so let's take a look at some cases. Okay, so case 1, we're looking at if this thing is finite for at least one of them. Right, so that is not all of these things are all of x. Okay, so if that's true, then we can say that our intersection of all of them has to be a subset of this particular one. And let's maybe, oh, that should be an I, excuse me. So if this is finite for at least one of them, then our arbitrary intersection of all of them has to be a subset of this one in particular. And we know that subsets of finite sets are finite. So therefore, this thing, this arbitrary intersection, which was equivalent to the complement of the arbitrary union, has to be finite. Okay. So then case 2 is that x minus ui is all of x for all I. Well, if that's true, then the arbitrary intersection is just going to be equal to all of x. And so therefore x minus the arbitrary union is all of x. Okay, so that takes care of that criteria. And so then our last criteria, well, actually, let's go ahead and say that this tells us that this is in our topology, right? That's sort of an important step. Okay, so then now we need to look at the complement of the finite intersections. Okay, so again, by De Morgan's laws, this is going to be equal to the union of complements. Okay. And so here, since u sub I, so this argument is going to be very, very similar to what we had previously. Okay. So let's see how, I'm going to make sure I word this pretty similarly. So since we know that each of these is in our topology for all I, we know again that means that this is either finite or all of x for all I. Okay. And just like this case, we're going to have, or just like this criterion, we're going to have several cases here also. And actually this time, let's do sort of the trivial one first. So I'm going to say case 1 is that x minus u sub I is all of x for at least one I, right? Well, if that's the case, then the union of these guys is going to be equal to all of x. And so therefore x minus the intersection of these is going to be equal to all of x. Okay. right? So basically the idea there is that if x minus u sub I is all of x, u sub I had to have been the empty set, basically, right? So if one of those u sub i's is the empty set. All right, so then case 2, none of them is all of x. But all are finite. Okay. Well, we know that so we know that finite sets are countable. Actually, we don't even have to go into countability. A finite union of finite sets is finite is really kind of the best way to say this. So a finite union of finite sets is finite, right? We can make a one-to-one correspondence between that union of sets and a finite subset of the natural numbers. So therefore, this union of finite sets will have to be finite, and therefore the complement of that intersection will be finite. And so that gives us that our finite intersections are in our topology. And so since we have met all of our criteria, we know that the finite complement topology is indeed a topology.